Just saying it's in the order A, B.
Yeah, so what happens here is, that's right, it's in the order A, B. So if we're gonna left multiply A, if we're gonna left multiply B by A, and A has non-zero scalars on the rows like this, 1, 2, 3, and it's a diagonal matrix, which means it only has non-zeros there.
That's B or A?
That's A. What I just wrote is A. This right here is gonna be B. So if B is this, A, B, C, D, E, F, G, H, I, then remember how row multiplication works. This acts as a scalar on that row, plus this times that row, plus this times that row, which means we don't actually scale those other rows at all. So we're going to scale the first row, we're going to scale the second row, and we're going to scale the third row. Do you follow that? Because it's like these things act as scalar weights on each of the rows to build the new row. So I think, Noah, the way you reasoned through that was correct. So I would say that C is true. Yeah. Here, let me do a more concrete example. Can I? I think that would maybe help this a little bit. Okay, let's go with this. Let's go 1, 0, 3, 5, 1, -2, -1, 2, -3. There's going to be our left matrix A. Here's our right matrix B. Would you like letters or numbers? What do you think would be more clear?
Letters.
I think letters would help. Yeah.
You can't combine like terms.
Right. A, B, C, D, E, F, G, H, I. By the way, as I often do, I was asked to record and I forgot until just now. So we are recording, just so you know. Okay, here's how it's going to work then, right? To make the first row, I'm going to do a little work down below this, okay? To make the first row, we need to take scalar weights from the first row of A and use them on the rows of B. So I'm going to write this out really explicitly. It's going to be 1 times ABC plus 0 times DEF plus 3 times GHI. Now, I know that's an odd way to write the row, but it's going to end up being A plus 3G. That's the first element, A plus 3G. The second element is going to be B plus 3H. And the third element is going to be C plus 3I. I don't know why I wrote that so small, but that's it. Say again, what?
I just didn't realize we were doing it the other way. Okay.
Yeah, okay. So now I'll use a different color and show you the next row. Now we use 5 as a weight on the first row, 1 as a weight on the second row, and -2 as a weight on the third row. So it would be 5 times ABC plus 1 times DEF plus -2 times GHI. So to squeeze this in, let's delete this right bracket to squeeze this in better. It would be 5A plus D minus 2G. That's the first element. Then 5B plus E minus 2H and 5C plus F minus 2I. Sorry, that got really extended. And I'm going to skip the last row because I think you probably get it after seeing 2 rows. Everything I do today, I'll post a hard copy PDF and I'll post the video so you'll have access to it if you space out at any point. Questions here? Okay, thanks Noah for going. Izzy, could you do the next one? I see your pens are still moving. Hang on, let me pause. Izzy, hold up just a second. That's fine. Helps us take things in and think about them for a second. Could you try and make your writing nice? Just make it sloppy and you can write fast.
I'm also thinking through like
What's going on? Yeah. Okay, Izzy, would you please read us D and tell us what you think?
Yes, so D describes if BC equals BD, then C equals D. I think in one of our practice problems, we showed that as long as C and D have the same directrix, then BC will equal to BD. So it's not true that C equals D.
It's not true. You're saying it's false?
Yeah.
Yeah, you're right. It's false. I don't know what you meant about directrix, though. What were you saying about that?
Maybe I remember it wrong, but I thought it had something to do with directrix.
No. Oh, you mean dimensions. I misheard you. I thought you were saying the word directrix. Directrix. And I was like, we are not doing conic sections.
No, wait, determinant is determinant.
No. It's not determinant. What this has to do with is the invertibility of B. If B is invertible, then the statement is true, but there is no guarantee that it is invertible, right? Because if B was invertible, we could stick a B inverse on the left, and then those would cancel and we'd be left with CD. But there was a warning in one of our sections that said there's no cancellation law with matrix multiplication. Okay, so Izzy, you were right to say false, but the reason is because B may not be invertible. Any questions on D?
If it's not convertible, how is it not same still?
Okay,
It
what?
would be the same scale as being multiplied,
Okay,
no matter what.
it would take us some time to design one that will show that it doesn't work, but
Probably could just point you to the text.
we could do it.
Couldn't it also be like, if there's a free variable, so if C and D are multiplying, are all the same except for like two scalars, which are flipped in C and D. But if there's like a free variable in B.
Sorry, Hugh, hang on. When I'm processing his question, I'm not listening to you, so just hang on one sec. Let me look something up. No, I want to hear what you're saying. I got one. It's if you want to try one, it's number 10 on page 102 that shows you why this is false. Okay, all right, Hugh, go ahead, go again.
Well, I was gonna say there, because invertible matrix, part of that theorem is that columns B have to be linearly dependent from one another.
Correct.
So I was gonna say there could be a free variable within B
Okay,
that
yes,
that could be included in this. It's creating like that non-trivial solution. So say BC equals 0 and BD equals 0.
yeah.
One of those could be the trivial solution, and one of them could be a different solution.
I don't think that's okay to say because B and C are both matrices, as are B and D. So they're not going to equal the 0 vector. If they were to equal 0, they would equal a matrix full of zeros.
Okay.
So I don't think that's okay to
Okay,
say.
well, maybe not the 0 vector, but like in the fact that there could be multiple ways to reach the same number.
Yeah, I think that would be okay to say.
They're the same vector.
Joanna, could you read E and tell us what you think?
If A times C equals 0, then either A equals 0 or C equals 0. I don't think that's true because I think I don't know, I think I know that if you multiply the matrices using whatever method, so as long as each spot turns out to be 0, one matrix doesn't have to be completely 0, I think.
Okay, so yeah, so you're right, it is false. And the reasoning, we can go back to here and say, here, let's create a case where this happens. Let's make one up for real this time. So I want us to design two matrices such that their product is 0, but neither one of the matrices themselves is 0. So watch what we can do. We can call this ABCD. And should I go with all these variables? Maybe that's not a good idea. No, I think we can do this.
You should just start doing smiley
I
faces and stuff.
think we can do this. 5, -1, 2, 3. Okay, so watch, we're just going to set up a system. It would go 5A plus 2b equals 0. Right? And we could say negative a plus 3b equals 0. 5c plus 2d equals 0. And just lost my train of thought. Negative c plus 3d equals 0. Yeah, this will work, no problem. This is just solving a system like little kids can do in middle school. And this is just like solving a system like little kids can do in middle school. And so if we solve both of those systems, we're going to get, well, we should get non-zero. Let's check and confirm that we actually do. We could. I'm just going to do a solve command. All right, so 5a plus 2b equals 0. And, oh, actually, they may only intersect at the origin. Uh-oh. Negative a plus 3b equals 0. Comma a, comma b. Oh, shoot. Okay. So that's not good. All right, what did I do wrong, you guys?
Variables.
No.
Do they both have to be the same size, like both m by
Isn't
n?
it
Just
just
because you
easier
just do
if there's
one
any
ax
multiples of
equals
each other?
0.
Okay, I think you might have a point there. If this is 5,2 and this one is 10,4, I think that, oh, right, because neither matrix can be invertible, right? If AB equals 0, but B was invertible, then A would have to be 0. You follow me? Watch. If B is invertible, which it was in the example that I just showed, then look what would happen. We'd get A times the identity equals 0, which means that A would equal 0. So that would violate what I'm trying to prove. So as long as we change this and get infinitely many solutions, see, if we put 5a plus 2b and 10a plus 4b, now we've got infinitely many solutions. Because those two lines lie right on top of each other. That's how we would show it.
Well, hurrah.
Hurrah. Okay. Joseph, could you read F, please, and tell us what you think?
If A and B are n by n, then a plus b times a minus b equals a squared minus b squared. I'm not sure for this one.
Okay, let's work it out together, okay? So it was given as a plus b and a minus b. So Joseph, let's do the FOIL work together. We got a times a, right?
Yeah.
Got minus a times b. Then what do we have? Yeah, this is just distributive law. Then what's this product going to be?
AB
Nope, careful.
or BA.
BA. And then what's the last product going to be?
B negative B.
B squared, right? Yeah, it's going to be minus b squared, right? Here's the issue. Joseph, are these two quantities equal?
No.
Right. Not necessarily equal, right? So therefore, this is false. What this thing is doing is it's kind of a creative way of asking you to know if matrix multiplication is commutative or not. So we know that it's not. And so we would say this is false. Those inner terms do not cancel. Okay, G. I don't know G off the.
Can I see that one more time? Sorry.
Yeah. Go back to what I wrote. Yeah, sure.
No, you're good. You're not that tall. Yeah, you're good. Thank you.
Okay. Okay. Let's see. James Park, could you read G and tell us what you think?
An elementary n by n matrix has either n or n plus 1 non-zero entries.
Ooh, let's talk through them, James. Build me an elementary matrix that does the effect of switching two rows.
Is it 0, 1, 1, 0.
Good. And then do the rest.
1, 0, 0,
Sure. And the last row.
and 0, 0, 0.
0, 0. It can't be 0, 0, 0. It's got to be
Oh,
0,
one.
0. So what this elementary matrix does is it does the effect of swapping the first and second rows. All right, so this is type 1. This is a swapping kind. How many non-zero entries does it have? It has n equals 3 of them, right? Let's do a type 2, James. Type 2, let's call the kind where it scales up a row. So what would an elementary matrix look like that?
Just 2, 0, 0.
Yeah, 2, 0, 0, and then the rest of it would just be the identity, right?
Yeah.
Okay, how many non-zero entries does this one have? 3, right? Now let's do the last kind. So the type 3 would be the hardest kind of change, the one that takes a multiple of one row and adds it to another. So let's do that one as like 5. No, hang on. Let's leave the first row alone and let's replace the second row with 5 copies of this plus this row and then 0, 0, 1. So how many non-zero entries does this one have? It has 4. So I would say it's true, right?
Can you not make a scalar multiple of 0? Like, could you do n-1? Like, what if I wanted to erase a row?
Oh, no, you can't do that. I think that's defined, it's defined as multiplying a row by a non-zero scalar. Yeah. Okay, so this is true. G is true.
Can you go back one more time?
Yeah, back to here.
An elementary n by n matrix would imply that like you can only do one type sphere at a time.
That's actually how an elementary matrix is defined. You can only do one kind of change at a time. Okay. Done with that one. What was that? Was that G? Let's go on to H.
Cody, you got it.
Cody's got it? No, it's going to be Christina.
Oh, make sure you can see it.
I haven't looked now, dude. I got.
Oh, you've got your book. Okay. Christina, can you read us H and tell us what you think?
The transpose of an elementary matrix is an elementary matrix. I think that's true.
So her gut says it's true. Let's go back here and look. If we were to flip the rows and the columns of each of these, would it still be an elementary matrix? Okay, let's try this one. 0, 1, 0, 1, 0, 0, 0, 0, 1. Is it still elementary? It's the exact same thing. How about this one? 2, 0, 0, 0, 1, 0, 0, 0, 1. Yay, it's still good. I think her instinct might have been right. Let's check this one. 1, 0, 0, 5, 1, 0, 0, 0, 1. Is that one okay?
It's just a different element.
It's just a different elementary matrix, but it still is one. So good job. That one, I agree with you. I think that that's true. Okay, Julia, are you there? Okay, Maria, you can take it. Letter I, read it to us. Tell us what you think.
An elementary matrix must be square. I think that's true because you start out with an identity matrix and then you just like change one piece of it.
Very well said. You start off with the identity and you perform one elementary row operation. Could someone who is friends with Julia text her to come back to class? Make sure she's okay. I'm going to remove her. Oh, I know that never happens in here, but I do that in my other classes all the time. When you have a non-responsive kid, kick them out, see if they come back. All right, Michael, could you read us J, please, and tell us what you think?
Every square matrix is a product of elementary matrices. I think it's false.
Tell us why. Oh, this is a very cool question, actually. Let's see if you can do it, Michael.
Wait, every square matrix.
I don't know. That's just what I thought.
Your gut. Okay, this is cool. Let's talk through this.
A
What do you guys think?
Doesn't A disprove that?
Does A disprove that? No.
You don't have to multiply two elementary matrices.
Now, this is wonderful because what does it mean if you're a product of elementary matrices?
You're a transformation.
That you're a sequence of elementary row operations that can get there, which means that if no, because that would mean that every square matrix can be row reduced to the identity.
Oh, yeah, that's not true.
When can a matrix not be row reduced to the identity?
It's not invertible.
When it's not invertible. So this is false. That's false. And so your instinct was good, Michael. Every square matrix is not a product of elementary
You should just
matrices.
take the next test by intuition.
Yes, take the next test by intuition. Sangbum, read us K, please.
If A is a 3x3 matrix with 3 pivot positions, there exists elementary matrices E1 through EP such that EP through E1 A equals I.
Yep. That's great. Good. What do you think, Sangbum?
I mean, it looks true, but I'm not sure.
It looks true. Okay, it is true, Sangbum, and everyone, it is true. What this is effectively saying is it's giving you basically two conditions of the invertible matrix theorem. It's saying, okay, you've got 3 pivot positions. Great. That means that every other thing in the invertible matrix theorem is true. And one of the things in the invertible matrix theorem is that the matrix is row equivalent to the identity. And that's exactly what's being said right here, right? If you can take A and apply a bunch of E's to get I, then that means that it's row equivalent to the n by n identity. Okay, so that is true by the invertible matrix theorem. Okay, James V, can you read us L, please?
If AB equals 1, then A is invertible.
Careful, that's not a 1.
Oh, I.
AB equals the identity, then A is invertible. What do you say?
I think it's true, right?
It's true. Someone disagree with him and tell me why.
What if A is
Because
the
ornament.
Wait, B is invertible.
Nope.
Is the identity matrix invertible? Is A the identity matrix?
What does the definition of invertible matrix say?
That there is a C exists such that
Does A have to be square?
No, it has to be, well, correct. This doesn't say anything about being square, does it? So that poses a bit of a
It
problem.
wouldn't be an identity matrix if it wasn't square. It would.
No,
So A
could it-
could be invertible, but we can't say it's for sure invertible unless we know that BA.
Oh, yeah.
Wait, so we know the identity is n by n, right? So B could be a something by n, right? Yeah, you're right. It could be an m by n. And A could be an n by m. So since those are not square, they're not invertible. Only square matrices are invertible. Plus, it's got to satisfy both directions. We would have to say if AB equals I and BA equals I, then you have invertibility. So this is false. Okay. She's back. There we go.
If A is equals I and if B equals I, then.
Yeah, so the definition here, literally put in your notes or put somewhere that if you want to know the formal definition of invertibility, go to page 105. So it says an n by n matrix A is said to be invertible if there is a C such that CA equals I and AC equals I.
Page 105.
Page 105. Yeah, so it's got to be, both of those statements have to hold in order for something to be invertible. Yeah. A is invertible. So A is invertible if AC equals I and CA equals I. Sloppy handwriting, and why did I write it on the board?
Oh, that makes
Okay.
a lot of sense.
All right, M. James already went. Okay, so it's to the room. Carson, can you read us M? What do you think? You feel like it's one of the theorems? Someone disagree with him.
That feels wrong.
That's wrong. What should it be? You got it. It's the reverse. It's B inverse times A inverse. Yep. So AB inverse is the product of the inverses of the originals, but reversed. So that one's false. Okay, this N looks hard. Let's see. Bridget, read it to us. What do you think?
AB equals BA, and if A is invertible, then A inverse B equals B inverse A, or BA.
Yeah, whoa. I got to play with that. I don't know if that's right or not. Want to work through it with me? You feel like that's true? Let me go copy and paste this over to another page.
Well, maybe inverse. Would that mean that B would have to be the inverse of A?
I don't know.
So they just what we got the reverse.
Okay, ready? So if AB, so we're starting with this fact, AB equals BA. What should we do to both sides to try and get it to look like this?
Oh, multiply by
Take your time. My gut says multiply by A inverse over here. Multiply on the right by A inverse. Let's see where that takes us, okay? This takes us to A, B, A inverse equals B. You agree, right? Because A and A inverse go away. So now look, now we've got something that resembles this side, don't we? We just need to dump something else. Oh, I got it. What do we do now?
multiply by A inverse.
On which side? Good job. If we do A inverse right here, then we have it, right? B A inverse equals A inverse B, which is exactly what we needed. Ooh, that's cool. I'm going to put some of these on the test. These are neat. Well, I mean, it's just, okay, it's just number one, A through P. Just know your, be ready for some true and falses.
That's true. I just remembered.
This is a true statement. This is a true statement. True. But what's cool is I'm going to do true. If I do true and falses, I'm going to either make you explain why, or I'm going to make you fix the statement to make it true. Okay. I had this really easy chapter 2 exam that I gave last year during pandemic, and I opened it up and I'm like, there is no way I'm giving this one. It was all multiple choice, all on, what's that thing called? Exam login. Not happening.
Yes, please.
No. That means I got to be busy tomorrow writing a new exam. That's going to take a long time. Yeah, I know. I could just chill and watch YouTube and then give you the easy one. I know, seriously. Okay. Oh, Benji, read us. Oh,
If A is invertible and if R does not equal 0, then RA inverse equals A inverse.
what do you think?
That should be false.
I feel like you're right. Do you know why theoretically, or should we do an example?
I mean, I think it should be just that equals R inverse A inverse, I think, or I mean.
Yeah, like the reciprocal of R? Is that what you're thinking?
Yeah, I think that should be right.
Okay, let's try it. Okay, let's take a 2 by 2. Okay, let's just take easy one. 1, 2, -1, 4. Okay, that'll work. All right, now let's find its inverse. Okay, so this is A. Let's find A inverse. That's going to be 1 over the determinant, which is 4 minus -2. So 1 over 6 times, what do we do again? 4 goes there, 1 goes there, -2 goes here, and 1 goes there. So let's clean it up. It's going to be 2/3, -1/3, 1/6, and 1/6. We're trying to prove that RA inverse equals or does not equal, we're not sure, R times A inverse. Okay.
Is R a scalar or
R is a scalar.
Okay.
R is a scalar, right? Yeah, and R does not equal 0. Yep. Okay, so let's multiply this guy by a non-zero scalar. So let's take the scalar 2. So what is 2A? Well, it's 2, 4, -2, 8. And let's find the inverse of that. So 1 over the determinant, which is 16 minus -8, right? So it's 1 over 24. Stick the 8 here and the 2 there, -4 and +2. So this is what? 1/3. So it's not going to be true, is it? 1/12 and 1/12. So yeah. So that's cool. Actually, this is neat to observe. Look, if we were to take 2 times A inverse, no, that it's actually 1/2 times A inverse, isn't it?
No, it makes sense. It's an inverse.
Yeah.
Inverse of the R.
You take the reciprocal of the R and the inverse of the matrix. This is what's actually true. That's garbage. Cool. Okay, so back to our original question. This was false, right? False. Okay. Here we go. Who's next? Cody, read us P.
If A is a 3x3 matrix, and the equation AX equals 1, 0, 0 has a unique solution, then A is invertible. I don't think that would necessarily be true. So just because it has a solution, that means that it's linearly independent. That's not the only requirement for an invertible matrix.
But wait a second. If AX equals 0 has a unique solution, how many pivots will we have in A?
3.
3.
Wait, it's not AX equals 0.
You know what I mean. AX equals that garbage. Sorry, I said that wrong.
Oh, then it won't have this.
So A has to have 3 pivots. So there's not going to be any free variable, and there's never going to be a free variable, right? So I think this is true.
Okay.
Should we just check that with the solution manual just to be confident? Because I feel a little funny about that. Let me look it up one second.
The reason I said no, like I thought there was something that feels like too easy almost.
Okay, hang on. Where's the solution manual? I got to find it. Here it is. Too many files. Do you all have a copy of this thing? I was waiting for someone to just quickly answer. Of course we do. We found it online.
Actually, no.
Well, I usually give you solutions anyway, so. Okay, what number was this?
1P.
1P.
Chapter 2 supplementary.
Oh gosh, that means it must be like page 76. So 1P says true. If the equation AX equals that thing has a unique solution, then there are no free variables. Oh yeah, which means that A must have 3 pivots. Oh, it sounds like your teacher knows something. Since A is at 3 by 3
I'm so glad.
by invertible matrix theorem, A is invertible.
Wait, so
I,
one more time. Yeah. What's the definition of invertible again?
okay, well, the core definition is this. A is invertible if AC equals I and C equals I. In other words, if there exists a C such that this works. But along with being invertible, you get those other.
Oh, and they're all like are logically equivalent.
They're all logically equivalent,
So
which
that
means
that if we know that it's linearly
Yeah.
independent, then it must be invertible.
that's right. They're either all true or all false.
Got it.
Good. Okay. Do we need a? I kind of need a break. You need a break. Okay, let's take 5 minutes. Everybody, scatter for a few minutes.
Run away!
Run away. There we go. Okay. By the IMT, yeah, sorry, Michelle. By the IMT, when A is invertible, then A transpose is invertible. Okay, now Yasui, help me more. What is this thing? This thing is a product of a matrix of 2 invertible matrices. Do we know that the product of 2 invertible matrices is invertible? That was a mouthful. In other words, do we know that this thing has an answer?
Yes.
Yeah, what is it? It's the inverse of B, right? Times the inverse of A. Okay, so that means this, that A transpose A is the product of invertible matrices. So its inverse is actually A inverse times A transpose inverse. But, ooh, what do we do with that?
What if you? What's the goal?
The goal is to show this thing right here.
Well, first we have to explain why.
We already did that.
What if you put the inverse on the right side?
Tell me what you want me to write.
Okay, put A inverse on the right side of A transpose inverse on the right side again. It's like all the way to the right.
Yeah.
Put the inverse there.
A inverse right here?
Yeah.
And put that over here as well then?
There, yeah.
Okay.
Wouldn't that you would get A inverse alone on the right, right? How would that?
No.
What if you put AT inverse?
Huh?
I don't know. Or, oh no, if you multiply by AT on both sides on the right, same, so if you change the A inverse that you wrote in as blue, times A transpose, then the A transpose is on the right side of the equation. The inverse
Oh,
A
yeah.
transpose,
Yeah,
you
and then you
cancel,
have-
and then you have,
Those cancels right
right? The,
there.
yeah, the inverse of A transpose times A transpose cancels. not cancels, that's the wrong.
They become the identity and the identity test.
I'm sorry, I'm confused. Can you
So,
slow
like-
down?
I'm just saying, because if you write these, then these two cancel, right?
Oh, yeah. Oh, yeah, smart. Good job. So A transpose A inverse times A transpose equals A inverse. Well done. Cool, good job. Thanks. Very nice, very nice. Okay, we have one problem left to do, and that's 15. And I'm sure you're all gonna be jazzed about starting a new unit after that, right? Forget it, I won't. Oh, just wait till next time. I was going to, but we won't. Okay. Yeah, it would have been probably pretty fruitless. All right, number 15, let's look at this. Okay, suppose that C equals E3, E2, E1B, where E1, E2, and E3 are elementary matrices. Explain why C is row equivalent to B. Just anyone can take this. Just speak if you know. 15.
What is C?
I don't know. Some matrix.
Elementary matrices are matrices that perform row equivalent operations onto a matrix. So it's just doing elementary operations. So like by definition, it's row equivalent.
That's right. Okay, so here's the formal way to say this. Let's type this out nicely or write it out nicely. Okay, so elementary matrices perform elementary row operations when multiplied on the left like this, like E1B or something like that, you know? What did I just write? Elementary matrices perform elementary row operations when multiplied on the left like E1B. And two matrices are considered to be, I just had a cool thought. Let me share it with you in a second. Two matrices are considered to be row equivalent when they, no, what's the right way to put this? When one matrix can be created from the other by a sequence of elementary row operations. Yeah, that's no, not when they were ref to identity, when they ref to each other, right? So two matrices are considered to be row equivalent when, yeah, we'll go with that, when they ref to each other, or maybe to just say when they ref to each other.
They're allowed to common matrix. It's the same.
Two matrices are considered to be row equivalent when they ref to, yeah, a common matrix, or no, they could ref to each other. They could ref to each other, I guess I should say.
They would mirror each other.
Yeah, one refs to the other one. That's right. When they ref to each other.
Wouldn't it be they can ref to each other?
When they can ref to each other, two matrices are considered to be row equivalent when they can ref to each other. Sure. That works. Okay, you don't want to start a new unit with 8 minutes left? Okay, fine. I will agree to that. Oh, my thought. I was thinking maybe I don't know, you'll probably not like this, but what if I made the exam like all like typing and reasoning instead of just doing problems?
That's gonna be really tough.
Because I mean, I know that would be harder, but it's so dumb to make you do problems when you have a calculator, you know?
I think it would be.
It's just so like fruitless, like, oh, okay, I can type this in a calculator and I'll get it.
I think there's a lot of.
That's the beauty in it.
Yeah, well, I mean, really, like, there were some problems that just, like, yeah, you can do it in a calculator, but you have to like learn how to do it, like.
Yeah.
Rotating
I
around
think
about a lot.
having to be able to do it over calculator, you also have to understand what's going on. So,
I know where you guys are biased in this. That's fine.
I don't know, I think that it, although like reasoning through it would be like maybe a better way to test our knowledge of it, I think that it'd be a lot harder to,
It would be harder to grade, wouldn't it? You're looking out for
It would also
me.
be harder to grade. And I feel like there's like it's such like there's no like middle ground. It would be very much either you know it or you don't.
Yeah, yeah,
It would
yeah,
be
yeah,
really
yeah.
hard to like.
Okay,
partial.
let me make a couple more comments. Okay, so I won't do that. That's fine. I won't do that.
Candy.
So I'm gonna ask you to sign a pledge 2 times during the exam. I've heard that, I've read some research on this or something, that if you ask someone whether or not they've been honest at the end, it's different than if you ask them to be honest at the beginning. So I'm gonna make you do it twice. So at the beginning, I'm gonna ask you to sign a pledge that you will not communicate with anyone else during the exam. And at the end, I'm gonna make you sign the same pledge. And I guess like, I mean, I know that might not mean anything to you, but maybe it gives you a pause, you know?
People
Maybe,
just lie twice.
yeah, I mean, I totally get that. I totally get that that's definitely a thing.
Maybe
And
if you did tell us that we were.
After I signed the first one.
Then we'd be like blindsided with another pledge.
yeah,
After the first one, I'm gonna work my way through the entire test and then come to the last one.
I mean,
It's
Mr.
gonna be
Coe.
like, you know what? And I'm gonna burn up my test.